Hello, my name is Clarence Mayotte. I am an application engineer with Linear Technology. I currently support high-speed ADCs. Today we will be discussing the LTC2261 high-speed data converter and some of the features that help simplify design and reduce digital feedback. The LTC2261 is a 14-bit 125 megasample per second ADC that consumes only 127 milliwatts of power from a 1.8 volt supply. It is a low power operation, improves thermal performance in compact enclosures and when using multiple ADCs. The low power consumption also improves battery life in portable applications. Let's take a look at the typical performance of the LTC2261. This is an FFT of the 14-bit LTC2261 sampling a 70 MHz sine wave at 125 megasamples per second. Our demo system measures a signal-to-noise ratio of 73.2 dB. We can see that the SFDR is better than 90 dB. This shows the excellent AC performance of the LTC2261 while using 1/3 the power of a comparable ADC. In addition to good analog performance and low power consumption of the LTC2261, it also has some unique digital output modes. The LTC2261 can be configured in 3 different digital output modes. The first, full rate CMOS, uses the lowest amount of power and uses all 14 data lines. Second, DDR CMOS uses 7 data lines by transmitting 2 bits of data on both the rising and falling edge of the clock. The third, DDR LVDS, also transmits on both the rising and falling edge on the clock and uses 14 data lines, but differentially, which gives some immunity to digital feedback and digital noise. Now I would like to show how digital feedback can manifest itself in the noise floor of an ADC. Here is a magnified screenshot that shows the noise floor of the LTC2261. Digital feedback typically produces a shaping of the noise floor as shown. In this case, the digital feedback causes peaks in the noise floor of about 3 dB. The layout of the LTC2261 demo board was optimized to minimize digital feedback, but still some is unavoidable. In applications where poor layout is used, these peaks can be up to 20 dB. If this were a narrowband application that happened to collide with the elevated regions of the noise floor, this represents a real loss of SNR on the order of 20 dB. While good layout can help reduce the effects of digital feedback, it may not be enough to eliminate the problem. The LTC2261 helps reduce digital feedback by providing a new proprietary mode to help mitigate it, called alternate bit polarity mode. Let's take a look at an example where digital feedback is likely to occur. In this example, we have a signal that is exercising a few codes around mid-scale. On each sample, all of the high-order bits are swinging from 0 to 1, which generates large ground currents that can couple back into the analog input, maximizing digital feedback. When alternate bit polarity mode is used, every odd data line is inverted. This means that instead of 14 data lines switching between 0 and 1 together, half are switching in one direction and half are switching in the other direction. This provides a cancellation of ground currents to provide a significant reduction in digital feedback effects. To decode this data, a simple inverter would be needed to implement in the receiver on each odd data line. Here is an example of the noise floor of the LTC2261 with alternate bit polarity enabled. As you can see, the shaping of the noise floor is reduced, improving SNR and SFDR. An alternate bit polarity mode helps to reduce digital feedback, which can be critical in designs with low input signals or poor layout. In addition to alternate bit polarity mode, an optional data output randomizer is available to further reduce interference from digital outputs. Using the output randomizer and alternate bit polarity mode can significantly decrease the effects of digital feedback. The LTC2261 is part of a family of ADCs from 12 to 14 bits with sample rates from 25 to 150 megasamples per second, which consume 30 to 160 milliwatts of power at higher sample rates. For more information on this product line, please visit us at www.linear.com. Thanks for watching.